Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. I am Bill Farmer, and we're going to continue discussing the topic of first-order logic. We're going to start with Hilbert-style proof systems. So here is a Hilbert-style proof system for a first-order language L. And notice that we've included equality as a predicate symbol. The axioms of this system, which we're calling H prime, has the same axioms as our system H for propositional logic. That's here, but it has two quantificational axioms. The first says that for all x, A implies B implies A implies for all xb, and this is true provided x is not free in A. So if x is not free in A, we can push that quantifier through the implication to the antecedent. The second axiom is what's called universal instantiation. So universal instantiation basically says that if we have a universal formula, we can instantiate the quantified variable with any term as long as that term is free for x and a. In other words, as long as that term does not cause a variable capture. Now, there are also axioms for equality. And these axioms basically guarantee that equality is a congruence. And I'll remind you that we are assuming that in every interpretation, if equality is in our language, the interpretation must interpret equality as a congruence. And then this proof system has two rules of inference. It has modus ponens like the propositional version, and it has generalization. Now generalization says that if we've proven A, we can infer for all x dot A. Presumably in this case, x is free in A. So generalization represents the proof method where if you're trying to prove a universal statement, you pick out a value which is unspecified and you prove that the statement is true for that unspecified value, and then you can assume the universal statement is true. So x here plays the role of an unspecified value. Okay, now I've said before that H prime is an extension of our proof system H for propositional logic. So that means basically anything we could prove about propositional logic, we can still prove in H prime. So here are some metatheorems for H prime. Like for propositional logic, we have a deduction theorem. We have a soundness theorem that says whenever we can prove in H prime A from U, then that implies that A is an semantic consequence of U. And whenever we have that A is a semantic consequence of U, that implies that we can prove in H prime A from U. And then if we put these two theorems together, we get that U is consistent in H prime if and only if U is satisfiable. And we also get the compactness theorem, that if U is finitely satisfiable, then U is satisfiable. So these are all the same, these are analogs of the metatheorems we had for H, our system for propositional logic. Then there's some interesting theorems that we can derive. One is existential generalization. That says if a formula is true at a term t, then we can derive the existential statement, there exists x dot A. And this is provided t is free for x and A. And this is very easy because existential generalization is the contrapositive of the axiom schema A7, and which I called universal instantiation. Another theorem we get is for all x dot A implies there exists x dot A, and we also can prove as a theorem alpha equivalence. Alpha equivalence basically says if I have a universal statement for all x dot A, I can change the variable that's being bound. I can rename it to something else. Let's say y, provided y is free in A, not free in A, and y is free for x in A. In other words, what people sometimes say, I can swap out x and replace it with another variable y as long as that y has not really been used in any way in my formula already. And then finally, the last example is equality substitution. If I can prove, if we know that S equals T, and then we have a formula A, and we replace one occurrence of S with T, and then get the formula B, then we know that A and B are equivalent. And of course, that's provided that the occurrence of S is not the variable that comes immediately after a quantifier. Okay, so that's a quick overview of a Hilbert-style system for first-order logic. Let's go on now to Gentzen-style sequence systems. In first-order logic, we have sequents, which are very similar, essentially the same as sequence in propositional logic. Instead of being propositional formulas, they're first-order formulas. But the important thing is, if I have a sequent of this form, semantically, we think of it as a first-order formula of this form. So we think of it as the conjunction of the members on the left-hand side of our sequent imply the disjunction of the members of our right-hand side. And then we can, using this, define what it means for a sequent to be universally valid. It just means that the value of that sequent in any interpretation and assignment will be true. Okay, so here is a Gentzen-style sequence system, which I'm calling script G prime. The axiom script G prime are sequence where U and V contain a common formula, and then we have the following rules of inference. So far, this is exactly like our Gentzen-style sequence system for propositional logic. But we also have some additional rules for quantification. And these are given here. Notice that A left and existential right have very similar form, and likewise existential left and universal right have very similar forms. And there's a number of conditions that have to hold. Here, x can be any variable, but basically y, which occurs in these two cases, y must be a variable that does not occur in u, v, or w. It does not occur in A unless it's x. And it must be free for x in A. The important thing to see is that these two rules, existential left, universal right, these two rules are really correspond to Gen. If we go back up the Hilbert-style system, we had this rule Gen right here. Gen stands for generalization. These two rules correspond to generalization. Okay, and like H prime being an extension of H, G prime is an extension of G, which means anything we could prove in propositional logic, we can still prove in G prime. Okay, so we have a notion of deduction trees, just like for G. This is going to be this least set of trees that we get from taking one-node trees that are labeled by sequence and then closing up this set using the rules of inference we have. And the conclusion of a deduction tree is just the sequence that labels a root. And we say a deduction tree is a proof tree if all the leaves of the tree are labeled by an axiom. And then a sequent is provable, which we write like this, if there exists a proof tree for the whose conclusion is this sequent. So this is entirely analogous to propositional logic. Notice we didn't mention the notion of a counterexample tree. So here's the metatheorems. Now these metatheorems are true when we don't have equality. The problem with equality is that according to our assumption, equality has to be interpreted by congruence. There's no mention about a congruence. So these theorems are true when we don't have equality, the equality symbol. We could represent equality with another symbol, and it would be still, these theorems would still hold. So we have soundness. If we can prove a sequent, that means the sequent is valid. If we can prove it, then we know it's valid. We have this interesting search procedure, which says if there's no variable that is both free and bound in our sequent, then there's a procedure that if we take the sequent as input, if the sequent is valid, the procedure will stop with a proof tree for the sequent. If it's falsifiable, the procedure may halt and give us a finite tree, which is a counterexample tree, or it will generate an infinite tree. In this case, the procedure does not halt. It runs forever, but as it's running, it's creating an infinite tree, which is a counterexample tree. And both of these counterexample trees, they encode an interpretation which will falsify our sequent. So this is, unfortunately, we can't go into detail about how this search procedure works, but this is very interesting theorem. So compared to propositional logic, we had a search procedure, but that search procedure halts on all sequence. This will only halt on sequence that are valid. And then we have completeness. Again, if there's no variable that is both bound and free in our sequent, then if our sequent is valid, it implies that we can prove our sequent. Now, we can come up with another sequence system with equality. This is just like the one before. We're going to call this G prime sub E. It's just like the one before, but we add a whole bunch of axioms. Remember before, an axiom looked like this, where there was a common formula A in both of these. Now, in addition to those axioms, we're going to add a whole bunch of equality axioms. Here they are. If you think a moment, these are the axioms that say equality is a congruence. And then we have a whole similar set of metatheorems for G prime E. So G prime E is, it's a little more complicated than G prime because we have these equality axioms. And we don't have this wonderful kind of symmetry that we had before when we don't have equality. So the problem here is that we're treating equality always as a congruence. And that means we have to do a little bit more work to create a sound and complete Gentzen system. Okay, so that completes this lecture, and that completes our lectures for the topic of first order logic. So thank you very much. Goodbye.